Hello everyone and welcome to Chapter 3. In Chapter 3 we'll be starting to talk about integrals. That's going to be a big chunk of the class and we'll have a lot to say about it. Let's start today. In this video we'll be doing section 3.1.1. We'll be talking about antiderivatives. Alright, so the goal of section 3.1, which is going to be indefinite integrals, just to define the indefinite integrals of function and study some properties. Alright, so this is just the beginning of integrals. 3.1.1, I want to look at antiderivatives. Alright, so a function g of x is an antiderivative for f of x if the derivative of g is f. Alright, so when I ask you for the antiderivative, what I'm giving you, this f here, that's the derivative. Alright, so to get from g to f, I differentiate. But if I give you f and I ask you for g, then what I'm asking you for is the antiderivative. Alright, just to make sure everything is clear, let's try some basic example. Example 3.1.1, I want to define an antiderivative for the following function. In A, I have f of x, which is 1 over x. Alright, so our goal is to find g. So goal, find a function g of x so that g prime, this is what I want, g prime is f. So is f and f is 1 on x. So can you come up with the function whose derivative is 1 over x? Well, the one that comes to my mind is ln of x. So for ln of x, we could take it because if I take the derivative of log of x, I'm going to get 1 over x, which is f. Alright, so that's the function. So in Cal 1, we would give you ln of x and ask for the derivative. You would say 1 over x. Now in Cal 2, we give you 1 over x and we ask for an antiderivative. You come up with ln of x. Alright, so it's backwards from what we were doing in Cal 1. Alright, so now the next question is, can you come up with an antiderivative for cos of x? So we need a g of x whose derivative is cos. Sine would work, because if I take the derivative of sine, I get cos, I get f. Alright, next one. Can you come up with a function that's the antiderivative of 1 over square root of 1 minus x squared? Turns out we learned it in chapter 1. If you look at arcsine, its derivative we learned in chapter 1 was 1 over square root of 1 minus x squared. That's exactly f of x. So we did find our antiderivative. Alright, so let's try this one. I'm looking for an antiderivative for x to the 5. When we take the derivative, the power decreases by 1. And so here we want an antiderivative and we want to land on x to the 5. So we want the derivative of something to be x to the 5. So the first thing I'll try, I'm going to try g of x is x to the 6. Then when I take the derivative, I'm going to get 6x to the 5. So it's close, but not quite right, because I have that extra 6 that I didn't have in f. So I need to figure out how to get rid of this 6. Any ideas? What if I divide x to the 6 by 6? then when I take the derivative, that 1 over 6 just comes out, and then I get 6x to the 5. So adding that 1 over 6 doesn't change much, except that you actually get rid of the 6 that you didn't want here, and you do get f. So that's perfect. This one works. All right, let's try something a tiny bit more complicated. Example 3.1.2, check that g of x, which is minus log of cosecant x plus cotan of x, is an antiderivative for cosecant of x. Now, if I ask you for the antiderivative of cosecant of x, something whose derivative is cosecant of x, probably you wouldn't come up with anything. In fact, this is pretty much the simplest one. So coming up with this g would be a very hard problem. But once I give you g, if you want to check that this is an antiderivative, all you have to do, according to the definition, is check that the derivative of what I'm giving you gives you f. And so that's what we want to show. So we need to show that the derivative of this monstrous function right here simplifies to cosecant. All right, so let's take the derivative. I need the derivative of minus ln of cosecant of x plus, I'm even having trouble copying it down. So minus log of cosecant of x plus cotan. All right, when I take a derivative of a log, it's going to be 1 over f of x. That's the formula, 1 over x for the derivative of ln of x. But then because I have something more complicated inside, I'll multiply that by f prime of x. That's a chain rule. All right, so here I'm going to get minus 1 over this entire mess. And then I have to multiply that by the derivative of the interior. All right, so this is just a chain rule. All right, so I get minus 1 cosecant x plus cotan of x. Derivative of cosecant is minus cosecant x cotan of x. Derivative of cotan is minus cosecant of x squared. All right, I need to simplify this. The minus will cancel, and let me factor the top. I have cosecant in both. So I'm going to get cosecant of x. I have cotan of x and cosecant of x left. But that turns out, almost magically, to be exactly what I have in my denominator. So this and this will cancel, and I'll be left with just cosecant of x. All right, so I showed that if I take the derivative of this, I get cosecant. So I did show what I was asked. I showed that this big mess was an antiderivative for cosecant of x. In fact, we'll see in a couple of classes, a bit more, in fact, we'll see in a couple of classes maybe, and a bunch of videos, we'll see that the integral of cosecant will be something like this, and this is where it comes from. All right, let's do the next example. Example 3.1.3. I want to find 3 antiderivatives for f of x equals 1. All right, that means I need to find 3 function g, so that g prime of x equals 1. All right, so can you come up with a function whose derivative is 1? Well, the obvious one is just x. because, I mean, x is a line and its slope is 1, so the derivative would give you 1. Right? But we need to find 2 more. Well, what I just said would work for any line of slope 1, so I'm going to take a second one. I'm going to take x plus 1. I could take x plus 2, I could take x minus 1, whichever one you like the best. I could take x plus 5 or 20 or pi, whatever constant I want. All of these have the same derivative, and so all of these are antiderivatives for the same function. All right, so the takeaway from these examples, well, from example 3.1.2 is that finding antiderivatives is hard. It's hard, but once you have the answer, it's not so bad. So easy-ish to check if g of x is given. And then from example 3.1.3, the point was that a function has many different antiderivatives. So there isn't a single antiderivative for a function. All right, so the following proposition looks at how the different antiderivatives of f of x relate. So this proposition, I'm going to call it fact C just because I find it easier to remember than any other name. So if g1 of x and g2 of x are two antiderivatives for the same function f on an interval, then there exists a constant c so that g2 is just g1 of x plus c for all x. All right, so I drew a little picture here. That means that for any point, the difference between g1 and g2 is c. So this entire graph is just shifted up. So the slopes are the same everywhere. The tangent lines will have the same slope, and that means the derivatives are the same. So knowing f, knowing the derivative, gives you the general shape, but you could still move it up or down. I could draw one here or here or here. As long as I keep the same shape, they're all going to be antiderivative. All right, so the only freedom is what I've done here of adding a constant. That's all you can do. All right, so that's it for this section. Next, we'll define the indefinite integral.